Hello everyone, we're here at UTAC today. I'm here with Don Wright of Unico and Dustin Harrison of UTAC. And Unico has a rather large equipment installation here, and we're here to see how some of that stuff is put to use and how that relates to all of us in the electrification business.
Yeah, so thanks for inviting me onto a video. We did a podcast a few months ago. It was great. And we wanted to kind of show you a little bit of the technology that we talked about in our podcast. And what better example than coming here to UTAC out here in Northville, Michigan. And so thanks, Dustin, for letting us come out here. Maybe we can talk a little bit about what UTAC is doing here and some of your facilities globally.
Yeah, very excited to have you guys out. Take a look at what we have to offer here from our testing capability here in the Michigan facility. We're going to look at some e-motor test stands today, as well as some EDU test stands and general durability that we're doing within our current facility. And hopefully we can kind of get you up to speed on what we're doing and where we're going.
All right, sounds good. Let's do it. All right, we're here in a UTAC test cell, and we have lots of Unico equipment. We can't show you the device under test, but that's okay. We can see lots of equipment, and we can describe how it would be tested and how the equipment accommodates that. So Don, why don't you show us what's in these cabinets and tell us about how they work.
Okay, well, first of all, I think this is a really cool test bed to be in. Because it used to be an engine test cell.
Absolutely.
Then you guys, of course, with all the electrification work that you guys are doing, you converted it now to an e-motor test bed.
Yep.
And of course, this is a very special room because it's extremely high speed, one of your high speed dynos. It's actually a special dynamometer. So this is the electric motor that then loads down the e-motor from the customer to provide the load profiles that it needs for all the different testing. So this is a special dynamometer from a company called Dynamic E-Flow. It has special electrical windings in there that actually run cooling through the windings so that you can have very high power, very high speed in a very small size. So, and then pairing that up with that is our brand new silicon carbide Unico drive system with a silicon carbide battery emulator. We'll open those doors in a second, but maybe you can talk a little bit about how an e-motor test bed is utilized by UTAC for your customers and what they're doing in here.
Yeah, absolutely. So what we got here is basically an ultra high speed motor that is being powered by the Unico drives. What this enables our team to do is perform motor development testing on the inverter and work on calibration work with regards to where the motor's going, how quickly it needs to accelerate, what it needs to look like in the vehicle. They'll bring cals from the vehicle to test out on the bed to ensure the motor is responding the way that they expect it to do. We'll do the initial calibration and characterization of the inverter to make sure the latest and greatest technology is working the way that they expect it to. Our team will then develop and deliver test data based on that information. That test data is then used to kind of write and develop where it's going to go and what it's going to do for the vehicle. And ultimately, with the power and efficiency that we expect and get out of it, will help us to determine where we go from there.
So Dustin, the testing part of it could certainly be you come in with criteria, you run the test, and it's done.
Yep.
But it could also be development where the software engineer might be here and go through iterative tests trying to optimize the inverter performance, maybe.
Yep, absolutely.
Trying to max out efficiency is a common one, trying to get higher speed beyond base speed with flux weakening or field weakening as it's called. Is that a common thing for you to be working with the developers?
Yeah, so essentially on what we'll see and what we've kind of walked through here, this is basically the high end of what we offer from an engineering perspective. So you're kind of doing everything that there is. So you're kind of doing, we'll have software engineers in here working. Sometimes they'll have an issue from in-field calibration work where they need to verify, why is this thing accelerating in a wonky way when we put it on the track in a certain condition. So we'll start to really get into the calibration of the inverter, the tuning of the motor to make sure we get that efficiency out of it. We'll do things like shock, where we'll put really cold liquid through the inverter, see what kind of response we'll get out of that. One of the things that we see developing quite a bit over the last couple of years is thermal dynamics, and how does that impact the performance for the vehicle. Obviously we talk about some of the charging issues when it's cold. They want to see and make sure what does the motor and what does the inverter do when it gets that cold. What happens when the glycol's at minus 40? What happens when the glycol's at minus 20? What happens when we cycle it through a high temperature to a low temperature? Those are all the different pieces that we're going to kind of work through with the manufacturer of the component, but more importantly, what we're going to help them to actually drive for their end user, which is ultimately each and every one of us driving these vehicles around.
Yeah, a lot of people have underappreciation for what it takes to mate a motor, or e-motor as it's called here, with an inverter and optimize their mating, if you will. It can be a simple mistake that happens a lot in the industry, where you get a motor and you get an inverter and you connect them together and you go, oh, hey, look at that, it spins. Let's go do something with this. When in fact, you got 6 months to a year to dial this thing in to get it optimized.
Yeah, and absolutely. We 100% saw that at the beginning, no doubt, where it'd be, one manufacturer was buying the inverter from XYZ company and they were getting the motor from ABC company. And they said, cool, we're going to mix all those two together and everything should be fine. We just got to plug it in, right? Well, that's not actually how it works in the real world. We've got to actually do a bunch of calibration work. We've got to do a bunch of engineering work behind the scenes to make sure that thing's actually going to perform the way everyone expected it to. Mix that with, we talked about efficiency. That's a huge issue, right? If we talk about the battery drain and what we can do with the vehicle and the mileage that we can get out of it, right? So, that range anxiety piece, we got to make sure, what does that actually look like when they're driving down the highway? What does it actually look like when they're doing different things? And what they'll do here is, since they're strictly working on the motor, they'll figure out where is the motor its most efficient and how do we keep it in that range the longest in day-to-day driving.
So you see, claims to fame like Lucid's recent, their statement of efficiency that they just came out with, which was 5 miles per kilowatt hour.
Yeah.
Wonderful claim, and probably some of the best bragging rights in the industry, but a lot of people don't appreciate what it took to get to that level, and it is a lot of hard work in a cell like this that gets you there.
Yeah, absolutely. And obviously we spent a ton of time working and helping to develop kind of where that goes. I think obviously they looked at different things like aerodynamics. They looked at different things with regards to the vehicle design, but also they looked at how does the inverter perform? How does the motor perform? What does it look like under load? Those are all the different things that people are kind of trying to evaluate here. And if we can measure at a very high level here, it makes it much easier to then transport that to the vehicle. And I think one of the things that's very interesting when it comes to the motor development side is kind of what they're able to get out of different motors, right? So they're able to push the envelope of what it can do and, give you some of those bold claims of, we can accelerate at extremely fast rates, maybe not every day, not every time, but we're able to get these really big runs, and we'll do a lot of those runs here to make sure, will the motor sustain that for the long term? Will it last? We talk about durability, but ultimately this is all building towards a vehicle that's going to last in the market and really work for the team that's actually driving it.
Let's take a look at some of the things around the room here. Start with this bed plate we're standing on here. It's mounted in the ground, and it has all these different attachment mechanisms that allow you to hook up different devices under test, as well as different dyno equipment and chillers, heaters, whatever you might need. Can you describe the flexibility of this particular cell?
Yeah, so Don mentioned earlier, this is previously was an engine test cell, so you'll see things like exhaust and CVS that are in here that are related to what was the old original drive of what this cell was. But what we found is the conversion on engine cells to motor development stands is actually really unique and really, really centralized to what our customer demand is. They want a secure area. They want it safe for their team to be able to operate in, so we kind of box it into this room. So that's kind of the starting point of this. Talk about the bed plate here. It's sitting on a large seismic mass, so there'll be a large concrete pad underneath this that's isolated from the rest of the building. So that's typically going to be 4 to 5 feet in depth, and then the full width of the test cell. What that enables us to do is run these things at really high speed. So on this particular one, we're running up to 25,000 RPM. And when you start to get above, and I've always kind of used it for me personally, it's always been around 10,000 is where you start to read and see a lot of issues with vibration. So vibration becomes hugely problematic as you accelerate all the way up to 25,000. So everything that we talk about, the design, the layout, the fixturing, this might only be making 1,000 Newton meters, but it's spinning at 25,000 RPM. So if we look at some of the fixturing and these bracketries, right, these are all heavy duty steel. This is all a part of the design. We have to do full FEA analysis on all of the equipment that go into one of these test cells because it's got to work the first time. So a customer doesn't want to come in here and then have us go, well, hold on, we got to do a little bit of engineering work to figure out if we can actually spin this. We've got to get it to spin the first time actually have it work and not have any issues related to vibration. So the bed plate becomes a huge part of that as we kind of go there. And we talked about, Don also mentioned on these DEF motors, they're liquid cooled, but they're liquid cooled in the jacket of the inverter or in the motor itself. So we've got a chiller back there that's going to keep this DEF motor cold and cool. We'll also bring in other equipment. So outside of this room, we've got the big chiller for the UUT, so we can go down to -40 to the inverter. So we need to be able to run all those different things, and we need to remain flexible with the way and the approach that we take in delivering to our customer, because they don't want to pay for the setup 25 times and, oh, well, this has to go to that cell. This one has to go to this cell to do this specific test. What we're enabling them to do here is basically you can run your full development program here, never have to leave. We can swap different engines or different motors in depending on what is needed. So, for example, these bracketries are set up in such a way that what we end up doing is we're running a 24-hour operation. So what we'll end up doing is we'll run one motor for the first part of the day. The next motor from the other day will come on. We'll put that on at night. We'll run the durability cycle to ensure that it's actually running the way the Cal team thought it would, while the other team is actually crunching the numbers for their previous Cal. They'll come back in the next day, put their inverter back on, put their motor back on, and we'll flip-flop those every day so that we get night ends up being our durability, and during the day ends up being all our calibration work. That basically drives efficiency. Obviously, these test cells are extremely expensive. So if we're talking about a total test cell cost, we're somewhere in the, around $2 million for the full test cell here. We need to be able to get maximum utilization out of that. So what we do is basically make it so that we can swap these in relatively pain-free. Our technicians will come in, take one motor out, put a different one in. That's basically driving our efficiency up for our customer, which then makes their cost per test hour cheaper. And that's a lot of what we're trying to do with our team here.
Very good. A little bit about power. As a e-motor test stand, if you will, it's a bidirectional system. You can feed the unit under test power, and it can generate power by spinning it. So, is there anything special about this chamber or test cell, or maybe facility-wide, that allows you to accommodate the big regenerative energy?
Yeah, and I think I'll push that actually over to Don, because I think that's a really good segue into what these inverters, and these are a very special inverter for us, first iteration for our team, but what they're enabling our team to do is operate at much higher speeds and much higher acceleration rates. But I think Don can talk to the bipolarity of the units that we're actually using.
Yeah, so thank you very much. So that's actually a great reason why I wanted to talk a little bit about the equipment that you see behind you. So as we talk about efficiency on the vehicle level, the efficiency from the battery to the inverter to the e-motor to get the longest range, Unico really wants to have the highest level of efficiency for our test equipment. And so what you see here is actually a system that takes power from the main grid and converts it to a DC bus. And that DC bus inside of the system then feeds to the battery emulator, which then comes out. That's these orange cables here. That's sort of acting like the battery pack from the vehicle. But that same DC bus is also then powering the dynamometer. So when the dynamometer is absorbing the energy from the electric motor that's under test, it's recirculating the energy inside of this cabinet to allow you to have almost a net neutral effect on the grid of the building. And so here, of course, we have an active front end. I can show a little bit. Maybe we can walk over here. And one of the unique things that UTAC does that we do for them is they really like having systems that can be operated like Legos. So we give them a bunch of different active front ends of different powers. They have DC sections, so the DC section acts as a battery emulator or a battery simulator. And then we have dyno sections, and we also have universal inverters. And so depending on the project that UTAC has, they can put these pieces together to create a test system that matches exactly what their customer needs. And so what you can see in here is this is the incoming power, and then this feeds this large active front end. So this converts the building 480 volts to a DC bus. And as you mentioned before, that power can be pulled from the grid, or if we're actually generating energy from the electric motor, or in the case of like if you had an engine, it would be returning that energy to the building. And then from there, the DC bus goes across over to our latest technology that we talked about in our podcast, which is our silicon carbide drives. So this is the DC section. So these 3 drives here are each 400 kilowatts of DC power. These ones can go up to 1200 volts. So we're also seeing in the industry, of course, as you guys have torn apart the Cybertruck and the Lucid and a lot of these other vehicles, the voltages are going up to 800 volts, 900 volts. And so we need to have a battery emulator that can go up to 1200 volts to emulate those batteries from those vehicles.
This video is brought to you by Munro Associates.
From new product development to teardown benchmarking, Munro offers comprehensive solutions. We specialize in reducing cost and weight, drawing from 35 years of experience to help you maximize profitability and elevate your projects. Contact Munro Associates today, and let's turn your next project into a success story. Munro, innovation starts here.
So this is a DC section, and then as you can see, it's fed off of the common DC bus. And then when we come over to this section over here, this is actually 4 of our AC silicon carbide systems paralleled together to operate the dynamic e-flow dynamometer. So this is the absorbing side for the dyno, and as it's regenerating energy into the system, it is then going out to the electric motor over the battery emulator. And one of the things that we will then be working with to try to raise the efficiency even more in their facility here at UTAC is we're going to explore putting in a DC microgrid in some of their test facilities, which means that we could have multiple test cells powered from one active front end, because if you think about it, you only have to feed in the losses from the grid. And so we can have a larger active front end, stationary active front end somewhere, could maybe even be possibly connected to an energy storage system sitting out in the parking lot in a shipping container, so that any excess energy that you have can be stored in that large battery. And then you can then have only the DC sections next to all of the test beds. And we can't really film out in the production area because we have too many tests running out there, but what you can see is lots of durability test stands all next to each other. And if you had the ability to have a battery emulator and a dyno there connected to a DC microgrid, you wouldn't have to have so many active front end connections inside of your facility.
Sure. Our viewers would probably appreciate a little deeper dive into this statement about only having to feed the losses. So if you were just providing power to the device under test, there'd be a great load from the grid to do just that. But because it's an e-machine and it has the ability to absorb that energy and turn it back into electricity, it could go right back to the grid. But because this has a local DC bus, you don't have to go outside this room to be able to manage that. And the difference between the power it can generate under a test and what you feed it to have the test is that loss you're referring to. So it could be that you feed it the losses that just this room needs,
Yep.
or on a greater scale, as you described, with a little microgrid. That would be wonderful to be able to do that on a multi-test cell basis. That'd be very cool.
Yeah, it's really a hot topic right now as more and more battery facilities get built up, especially in North America, on the West Coast, but anywhere. There's a lot of energy that the facility needs, and if you have to go to your local energy company and say, hey, we need a 20 megawatt substation outside, it's going to take a long time to get the required energy. If you can keep that energy local, and as you discharge and charge batteries or run electric machines, and you only need to feed in the losses, and have the ability to save the energy if you have excess energy. Kind of like if you have excess renewable energy, you want to save it, put it in an energy storage system, and we can do that. So we can have a DC microgrid inside of a facility, and then at each test station, you only have the active section that you need, DC section, AC section, combination of the two. And for facilities like UTAC, where they're already utilizing, our quantum controller, where we can mix and match different power sections, we talked about it. We can have 2 dynos one day. We can have 4 dynos the next day. We can have 1 dyno and a battery emulator. Or maybe there's 2 battery emulators for a front axle port and a rear axle port. They have the flexibility, and they just move this equipment around and connect them up as they see fit. And so that's why it's really a great partnership between us to be able to enable them to do that.
So with regard to that energy, I can only imagine the worst case scenario of a facility like this with a bunch of engine dynos running on gasoline and diesel, where that's the energy.
Sure.
And now the absorbers have to turn that back into something, either heat, where you can dissipate it in the atmosphere, or electricity, where your local power company has to be able to accommodate that. Sure. And that is no small undertaking from my experience. So. It's much easier with just e-motors.
It is much easier. I think we talk about the grid and the grid capability. I think that's a huge, huge challenge for any new facility coming online right now. So when we're talking new capability or adding on more test cells, right, you got to make sure you have the ability to deliver the power to the vehicle or to the unit. Ultimately, that needs to come from the grid at some point. What we've seen on some of these facilities is, while this might be a 600 kilowatt setup, so it can theoretically use 600 kilowatts of energy, we're not actually using that at any given part of the day. So when we start to do any of those calculations, if we work with DTE here locally, when they start to do those calculations, they want us to know what kind of motors are you going to be running, how much, what's your cycles that you're going to be running them on, and they want to do a calculation. You have to sit there and go, wait, pause. You don't quite understand how our setup works, because we're actually regenning all of this. So I don't actually need 800 kilowatts for this test cell to be able to operate. I only need, maybe I'm picking up 100 amps of 480 to make this work. And that's able to do that here locally. That enables us to actually be able to make things happen. If we had to get power for every one of these stations and get it from DTE, we'd have to move next door to the nuclear plant, I guess. And that'd be kind of one of the challenges that we see. And we talk about time. When we just moved into this facility about 2 years ago, one of the key reasons why we selected this site was because of its feed of power. We were actually bouncing between 2 different sites. One site didn't have power, one site did have power. That timing basically was a 2-year window to get the power at the other facility. That didn't align with our timeline, so obviously we had to make some alternative changes and switch to this facility.
Interesting. So Don, you talked a little bit about the DC bus and the battery emulator. That's probably a subject worth diving deeper into. Give you my simplistic approach. You've got a power supply. There's AC that comes in and delivers DC out, and it kind of looks and behaves like a battery a little bit. But then everything changes when you're trying to charge that virtual battery, and now the power flow goes in the other direction. So it's one thing to set up like a fixed voltage and say, okay, we're going to run this test at 500 volts, and you can probably dial that in so it's 500 volts plus or minus a volt or something like that. Or you can emulate the actual battery pack, where you can bound your system by the constraints of the battery pack design. In other words, let's limit it to this many kilowatts, let's limit it to this many amps. Can you describe that? Is that something that UTAC can configure themselves, or how does that work with battery emulator?
Yeah, so that's a great question. So a lot of times there's kind of 2 different operating modes. So if you're the inverter company, or if you're the inverter engineer or the electric motor engineer, maybe you want to understand exactly how is my electric motor and inverter running at a very specific voltage. So we want to have a very stiff voltage supply. So if I set it at 400 volts or I set it at 800 volts, when I demand a current or I'm pushing a bunch of current back to that battery emulator, I don't want it to fluctuate very much, because I really want to understand what is really the effect, the efficiency, the power capability of my electrical component. So that is sort of one mode of operation. And there we have a great system that really gives us a stiff voltage. It reacts to what we call a disturbance very quickly to maintain that very stable output voltage. But like you said, Now that's the first part of the equation. Once you start integrating it with the rest of the vehicle, mainly the battery, you need to be able to replicate the voltage drop based on the state of charge, based on the state of health, based on the temperature of the battery pack. So this is sort of like a pre-integration work. And what we have some customers do is they have a battery pack in a completely different division of the organization, and they test them on a Unico test system. They test those battery packs in climate chambers. They test them at different states of health, different states of charge, different temperatures, and they get the profile of that battery pack and basically the inner resistance of the battery pack so that they understand when the inverter of the vehicle draws 300 amps at minus 20 degrees C and the state of health is 90%, the voltage actually drops from its nominal voltage down 50 volts or 100 volts. And then what we can do is parameterize our battery emulator to act like that. So we can have a control system, we can have a model, with our new quantum controller, we're enabling customers to put a battery model right inside of the controller, and it will emulate that voltage drop based on what demand of the current is. And that's really a pre-integration step, because then the next step would be is the customer would bring the real battery, the real E-drive, which is inverter and E-motor together, or E-axle, and then really see it on a powertrain test bed. So I think sometimes they have a real battery here. Most of the time they're doing battery emulation or battery simulation, and then doing this modeling capability. So you really, first of all, you want to, look at the efficiency and the power and all the capabilities of the inverter and the E-motor with a very stable source. And then if you want to do that pre-integration work, then you would start utilizing a model inside of the battery emulator.
Sure, and I can only imagine that having an actual battery in the loop, while that might have lots of pluses for certain types of tests, it's all the minuses about having to care and feed that battery, make sure it's charged, make sure it's fed.
There's safety, you can't run repeated tests, right? So if you run a test on a real battery and it gets down to 70% state of charge, well, now I have to charge it back up. Now is the temperature right? Is the BMS happy? Are the contactor? So there's a lot of activities that go around making sure that the battery is in a happy state and where it needs to be to test with a real battery, which is why, I think 95% of the E-drive, E-axle, E-powertrain test beds that we sell are dynos plus battery emulators all in one system.
Yeah, it's probably important to note too, because a lot of battery emulation systems are standalone, and some companies that's all they make.
Yep.
Whereas in your case, it's all in one set of cabinets,
Yep.
and it's all integrated and sort of harmonized, if you will.
Exactly. So a lot of times the battery emulators will have their own grid connection. The dyno drives will have their own grid connection. There's issues if all of a sudden something happens and faults out with the battery emulator and the dyno systems don't know about it. Everything is in one system. It's all controlled from the main control system, and it's a harmonized system. And it also increases the efficiency of the test bed, so you don't use as much energy.
Very nice.
I think when you guys were talking about the simulation side of it, where you have the battery pack and it's being tested in a different location, and then you have in this case, the motor being tested here, and then we saw it there, the unit or the EDU without the electric motor setup. In theory, the things that we're now working on with our group is, and we talked about where our battery facility is in the UK. In theory, we now have the capability with our simulation team to basically run a battery in the UK, tell it how it's responding and pulling current from here, putting it over to that inverter, and I could have a guy running a simulator software where essentially he feels like he's driving a car on the track, mimicked exactly to the Millbrook tracks. So like we can do a lot of different things with regards to that. So you can start to tie the test beds actually together. Now, ultimately, from a customer standpoint, that's extremely complicated, extremely expensive, because now you have 5 or 6 different test beds. From a interest standpoint and from a where the industry is going standpoint, that simulation side is going to become more and more important as we kind of develop that capability.
All right, we're in the final checkout area for some of the UTAC equipment. You can see the Unico cabinets in the background. We're going to let Dustin talk about their equipment and how it works and how it's deployed here and tested and then ultimately shipped to their clients. And of course, Don can tell us a little bit about the Unico portion of that. Thanks.
Yeah, so what we have behind us is essentially a test stand that we're building for a customer. So similar to the test stand we looked at earlier, we will help a customer develop their capability to run their testing as well. So this will actually go out to a customer. They'll use it in their facility, run their equipment, and they'll own the equipment from a go-forward basis. So what we're doing here is essentially building it up, make sure it all works, verify that all the connections and all the areas of interest are taken care of and functional properly. Once we're at that point, then we'll ship it out to the customer, install it there. Obviously, we'll clean it up. It'll look a lot nicer when it goes in the customer test floor. We'll get all the trenchway and all the other things that happen as well. But for here right now, essentially is make sure we don't have vibration issues, make sure the dyno's controlled properly, make sure we can hit the torque and speeds that the customer demanded. Those are all the things we want to check out before we give it to a customer, so that we don't look silly when we deliver it on their floor.
And of course, as part of that installation, there's the celebratory commissioning where
Yes.
you buy off on the system having been installed correctly and working the specifications. So how long does that normally take?
So typically that's going to be a 3 to 4 week time period. So once we're all fully installed at the customer's site, probably we'll spend 3 to 4 weeks. It really depends on the complexity of what the customer is asking for. This one is one of the more complicated test stands in that it has 2 high-speed inputs as well as 2 medium-speed outputs that all need to make different configurations. So in this configuration, they're able to run a single E-motor development stand and another single E-motor development stand, or they can run an E-axle with a high-speed input, or they can run 2 high-speed inputs and 2 medium-speed outputs. And so that flexibility is what the customer is paying us for, right? Is they don't want to they can't afford to just buy, hey, this is the stand to run the random vehicle that we have, and it's going to work for the next year. These are, again, multi-million-dollar investments. They want it to be able to run anything that they have in their program. So they need to be able to have that flexibility within their team as well. And we're seeing a lot more of that request coming from our customers when it comes to the test stands. Flexibility is really, really important because we only get so much capital money before somebody comes back to us and says, hey, you're all out of cash. What are you going to do next? Now, the engineers and us know that we need to get all the testing done so we feel comfortable in the product. And so they want to have this maximum flexibility as their key driving point.
Yeah, and of course, as you mentioned, so we have our Unico drive system in the back. So this is completely built and tested in Franksville, Wisconsin. So we build the whole system up there. We have similar motors that we would then have on site. And then we ship it here to UTAC. And then we work together with UTAC to integrate the whole system together, make sure it's all functioning for our end customer. And then this then goes out. And of course, at that point in time, especially with UTAC, they have the ability to commission our systems by themselves. But if we need to help them, we go out there with them on site for the installation and commissioning.
So generally your commissioning is here where it's all made together.
Exactly.
I got it. Very cool. Very impressive looking equipment as well. It's nice to see it when it's shiny and clean.
Shiny new and just about to go get messy and dirty.
Yeah.
Well, that's the nice thing about electrification. You don't have the exhaust, you don't have fuel, you don't have lots of stuff like this. So, it's quite nice. You do see, E-motor and E-axle test beds after several years, and they still look like brand new. So.
It's interesting to me all the different ways a dynamometer can be configured. We've got everything from connecting directly to the UUT as like a single motor, all the way to, in this case here, the ability to drive the hubs of the wheels on a vehicle.
Yep.
And a lot of people probably don't appreciate the difference in that the torque that's at the wheels is so much higher. That's why these machines are so big, and so that they have the flexibility of doing both that extreme low speed, high torque, as well as the higher speeds that are found on the motor side of that equation. So, I liken that to a whole new level of flexibility to think that this could be configured for both. It makes me want to experience that. And I'm thinking, I wonder if I could get Sandy to let us use the Cybertruck for an interesting experiment over here and see if we can do a couple dyno pulls on it, but we'll see.
Yeah, absolutely. Yeah. We'll look into that. I think that's certainly an opportunity for us to move forward with some unique looks at how we test and what we actually do, and actually see a full pull on the Cybertruck. That'd be amazing, right?
It would be fun. All right. Well, I think that pretty much covers our trip to UTAC, and thank you, Don, and thank you, Dustin, for such a great explanation of what you do here. I think our viewers are going to enjoy it.
Yeah, absolutely.
Yeah,
Look
thank
forward
you.
to it.
Thank you, Tom. Thank you guys for coming out, and I'd love to see the Cybertruck up on the powertrain test bed. That would be awesome.
Absolutely.